Hello everyone and welcome to this session on 8086 signals. This session is a part of the course CS305 Microprocessors and Microcontrollers for the 5th semester BTech Computer Science and Engineering students under the APJ Abdul Kalam Technological University. Myself, Anu Maria Joykuti, Assistant Professor, Department of Computer Science and Engineering from Rajagiri School of Engineering and Technology. Let's start with an overview of the 8086 microprocessor. The 8086 microprocessor is a 16-bit CPU which is available in 3 clock rates for the various versions, which are 5, 8 and 10 MHz. It is packaged in a 40-pin dual inline package and it has got 2 operating configurations, which are the single processor or the minimum mode and the multiprocessor or the maximum mode. This figure shows the pin configuration of the 8086 microprocessor. As we said earlier, there are 40 pins in the 8086 processor, starting from pin 1 to pin 40. The signals that are associated with each of these pins are written on either side, and there are 20 pins on one side and 20 pins on the other side. Now, as we can see in the figure, there are certain pins which has got 2 set of signals associated with it. That is, from pin 24 to pin 31, there are 2 set of signals that are associated with this. So it is evident from the figure that there are 3 categories of 8086 signals. Now, like as we said before, the 8086 signals can be categorized into 3 groups. The signals which are having common functions in both the minimum and the maximum mode, the signals that have got special functions in the minimum mode, and the signals that have got special functions in the maximum mode. First, let us look at the signals that are common for both maximum and minimum modes, starting with the address bar data lines, which are denoted by AD15 to AD0. These are time multiplex address and data lines. Now, as we all know, the 8086 microprocessor supports 20-bit address and 16-bit data. So, these lines are used for both address as well as data, that in a time multiplex manner. That means at certain time instance it will act as address line, and at the other time instance it will act as data lines. How is this being distinguished? This is being distinguished by using the clock states. That is, during the T1 clock state, the 16-bit address will be available on these lines, and during the T2, T3, T4 and TW clock states, it will be the 16-bit data that will be available on these lines. The TW is a wait state. These are active high signals. Coming to the address bus status lines, which are denoted by A19 to A16 or S6 to S3. These are again time multiplex address and status lines. Like we said before, during the T1 clock state, the 4-bit address or the higher order 4-bit address will be available on these lines, and during the T2, T3, T4 and TW clock states, the status signals from S6 to S3 will be available on these lines. So, the address lines together with A19 to A16 and AD15 to AD0 will form the complete 20-bit address. Coming to the status signals, the status signal S5 is used to show the status of the interrupt enable flag. And the status signals S4 and S3 combinedly indicate which segment register is currently used for memory access. For example, S4 and S3 is having a value of 00, it indicates that it's an alternate data register that is being used. If it's 01, it is a stack register. If it is 10, it is the code register. And if it is 11, it is the data register. The S6 status signal is always at a logical low because it is being reserved for future use. The bus high enable or the status signal, which is denoted by BHE bar or S7. The bar indicates that it is an active low signal, and the bus high enable signal is used to indicate the transfer of data using the higher order data bus, which is denoted by D15 to D8. The BHE bar signal is low during T1. So this is also a time multiplex signal where during T1 the BHE signal is available, and during T2, T3 and T4 the status information, that is S7, is available. Next we have the read signal, which is denoted by RD bar. Again, this is an active low signal, and when it is low, it indicates that the processor is performing a memory or IO read operation. The ready signal. The ready signal is an acknowledgement signal from the slow devices such as IO devices that it is ready for the data transfer to happen. It is an active high signal, and when the signal is high, it indicates that the device is ready for the data transfer to happen, and when it is low, it indicates that it has to wait. Next we have the interrupt request, which is denoted by INTR. This pin is being checked during the last clock cycle of every instruction to determine if an interrupt request is available by the processor. And if it sees any such interrupt request is pending, then the processor goes to serve that interrupt and it enters into the interrupt acknowledge cycle. This is a level triggered input and it is also an active high signal. The test signal, which is denoted by TEST bar. This signal is examined by the wait instruction, and when the signal is low, the execution will continue, and if the signal is high, then the processor remains in the idle state. Next is a non-maskable interrupt signal, which is denoted by NMI. This is an edge triggered signal and it is not maskable internally by the software. That means that it cannot be enabled or disabled by the program and the processor has to serve the interrupt. The clock input signal, which is denoted by CLK. The clock input signal provides timing to the processor for synchronizing various operations. This clock input signal is an asymmetric square wave with a duty cycle of 33%. The frequency of the clock input signal is different for the various versions of the 8086 microprocessor, that is from 5 MHz to 8 MHz to 10 MHz. The reset signal. This signal is used to restart the execution. The reset signal causes the processor to immediately terminate its present activity. This signal must be active high for at least 4 clock cycles for the reset to happen, and the execution will restart only when the reset returns to a low value. Next we have the power signal VCC, which is available on pin number 40. This is the plus 5 volt power supply for the operation of the internal circuit. Next we have the ground signal, which is available on pin number 1 and pin number 20, which is the ground for the internal circuit. Next we have the MN bar MX bar signal, which is the logic level that indicates what mode is the processor supposed to operate in. When the signal is high, it works in the minimum mode, that is the processor is to work in a minimum mode or a single processor mode. And when it is low, the processor is to work in a maximum mode or a multiprocessor mode. Next we will see the functions that are specific for the minimum mode operation of 8086. First is the address latch enable, which is denoted by ALA. The ALA signal indicates the availability of a valid address on the address bar data lines. It is an active high signal and it is connected to the latch enable input of the latches. Next is the data enable signal, which is indicated by the DEN. This signal indicates the availability of valid data over the address bar data lines. It is used to enable the transceivers, which are the bidirectional buffers, to separate the data from the multiplex address bar data signal. Next we have the data transmit bar receive signal, which is indicated by DT bar R. This output is used to decide the direction of data flow through the transceivers, that is the bidirectional buffers. When the processor is sending out data, it is high, that is data is being transmitted out. And when it is low, it indicates the processor is receiving data. Next is the memory bar IO signal, which is denoted by M bar IO. This is used to distinguish between the memory and IO operations. When the signal is low, it indicates that it is an IO operation that is being performed, and when it is high, it indicates that it is a memory operation that is being performed. Next is the interrupt acknowledge signal, which is denoted by INTA bar. This signal follows the interrupt signal, and when the signal is low, it means that the processor has accepted the interrupt request. Next we have the write signal, which is denoted by WR bar. This is again an active low signal and is used to denote a memory or an IO write operation. Now, whether it is a memory or an IO operation, it will be denoted by the M bar IO signal, which was discussed in the previous slide. Next we have the hold and the hold acknowledge signals, which are denoted by HOLD and HLDA, which is available on pin number 31 and 30 respectively. The hold signal indicates to the processor that the external devices are requesting to access the address and data buses. The processor acknowledges the hold signal by sending out the HLDA signal. Next we will see the set of functions that are specific for the maximum mode operation of 8086. We have the queue status lines, which are denoted by QS1 and QS0, which give information about the status of the code prefetch queue. They are active during the CLK cycle, after which the queue operation is performed. They are encoded as shown in the table. QS1 and QS0, if the values are 0, 0, this indicates that there is no operation to be performed. And if it is 0 and 1, it indicates that the first byte of opcode has to be fetched from the queue. Then if it is 1 and 0, it indicates that it's an empty queue, and if it is 1 and 1, then it indicates to fetch the subsequent byte from the queue. Next we have the status lines, which are denoted by S2 bar, S1 bar and S0 bar. These status signals reflect the type of the operation that is being carried out by the processor. These signals become active during the T4 of the previous cycle, and they remain active during the T1 and T2 of the current bus cycle. These status lines return to passive state during the T3 of the current bus cycle. Let's see what these signals indicate. Now, if the S2 bar, S1 bar, S0 bar is having a value of 000, it indicates the interrupt acknowledge operation. And if it is 001, it indicates an IO read operation. 010 indicates an IO write operation, and 011 indicates a halt state. If it is 100, it indicates an opcode fetch operation, and if it is 101, then it indicates a memory read, and 110 indicates a memory write, and the 111 indicates a passive state. Next we have the lock signal. When the signal is low, it indicates that other system bus masters will be prevented from gaining the system bus. The lock signal is activated by the lock prefix instruction, and it remains active until the completion of the next instruction. Next we have the request bar grant signals, which are denoted by RQ bar GT0 and RQ bar GT1. The request bar grant signals are used by the other processors which are requesting the CPU to release the system bus in the maximum mode operation of 8086. When the signal is received by the CPU, then it sends out an acknowledgement. The RQ bar GT0 has higher priority than RQ bar GT1. And that's all we have in this session. Thank you everyone.